Okay, hi everyone. So this is the first theory lunch talk of the semester. We're very happy to have Noah Golowich here from Microsoft Research, and he will talk about sequences of logits and the low-rank structure of language models. Let's give a round of applause to Noah.
Yeah, thanks for the introduction. Thanks for having me here. So I'm going to be talking about some papers based on joint work with Alan Liu and Abhishek Shah. As I'm sure you're all aware, LLMs have had large impact on the world already. They've increasingly had many commercial uses, and they're becoming more and more able to come up with new solutions to math problems, to science problems, and many other areas. But despite all these existing advances and the promise of many additional advances in the coming months and years, there are, of course, many significant risks associated with them. And there's been various papers that have highlighted some of these risks in the last few years or months. It's been observed, for instance, that language models can sometimes deceive us in terms of what they're trying to do. It's different from what they claim they're doing and what they're actually doing. And there's many other situations in which we don't fully understand what these models are actually doing under the surface. And moreover, many of the abilities of LMs to actually solve problems that we want them to solve remain somewhat mysterious. So in light of these challenges, one big problem is to come up with simple abstractions of LMs. On the one hand, are realistic enough to support testable predictions, and hopefully can be verified empirically. And also, on the other hand, are tractable or simple enough to enable provable guarantees. And that's going to be the main focus of this talk. So in the first part of the talk, I'm going to discuss one such universal abstraction, which I'm going to focus on, which is the idea that LMs, a certain matrix associated to LMs has low gradient in positive sense. I'll then formally define what I mean by this and give some empirical evidence that this actually holds. I'll discuss the theoretical result that we have in terms of learning such things in a provable sense. And finally, I'll give some additional empirical applications that give some evidence that the theory that we have actually predicts some of the observations that we can. So before continuing, I just want to fix some notation and terminology pertaining to LLMs. In general, a language model is defined over a vocabulary, which I'll call sigma. And to keep things simple, I'm going to fix some sequence length. So formally speaking, an autoregressive language model, which I'll denote by P, is a mapping that takes as input a sequence of tokens, say y1 to t minus 1. You should think of this sequence of tokens as corresponding to a partial sentence. And then the language model P outputs a distribution over the next token. Think of the token as being just a word or symbol. Now, given such a mapping, there is a canonical way to generate from this autoregressive, which is just repeatedly sample from this next token distribution and concatenate the next token that we sampled to the sequence of tokens y1 to t minus 1. This induces a distribution over capital T length sequences, they're called y1 to t. And via slight abuse of notation, I'll call that distribution P as well. So I'm thinking of the language model P as both being this mapping as well as the resulting distribution over length T sequences. Okay, so let me go back to this question that I asked about obtaining simple universal abstractions of LLMs. One way that we might go about approaching this question is to study low-dimensional representations for languages. What do I mean by this? Well, here's one diagram. For any sequence of tokens H, think of H as being prompt. I want to find the compression phi of H into a d-dimensional Euclidean space, which in some sense captures all information contained in the prompt. Now, the idea of looking at low-dimensional representations of deep neural networks and language models is not at all new. People have studied word embeddings, sentence embeddings, document embeddings, and so on for many years. And there have been many successful companies that have been founded based on these ideas. But the particular properties that I'm going to want this embedding to satisfy, and the way I'm going to think about them are a little bit different from those of Python. So let me be a little bit more precise about what I want, what properties I want this embedding phi of h to satisfy. When I say it captures all information in the prompt, what I want is phi of h contains enough information so as to allow us to generate sequences from the language model conditioned on the prompt. Now, in more detail, I want this to also respect the linear structure in RD. And so the particular property that I want the feature vectors phi of h to satisfy is shown here. I want there to be some other feature mapping psi, which maps sequences of tokens to d-dimensional Euclidean space, so that for any sequence H, which I'll call a history sequence, think of it as a prompt. And for any other future sequence F, think of it as a response. The probability of observing the future given the prompt according to the language model is up to a normalizing constant, roughly x of the inner product of the two corresponding features. So this is a very simple probabilistic generative model that I'm positing for language models. And you might think that it's way too simple for it to be true even in an approximate sense. Because after all, I'm just saying that things are log linear. And over the course of the next few slides, I'm going to try to give you some empirical evidence, which hopefully will convince you that, at least to some extent, this approximation is actually true for an appropriate choice of the feature vectors phi's.
When do you mention the relative length of F and H and F?
The length, excuse me. Think of them as being roughly the same length. So we have experiments where they can think so they can do dozen tokens. But they can be, hundreds of tokens.
D is not small.
Well, D is going to be much smaller than exponential. So like D is going to be in thousands or something. But the number of sequences of length 20s is extremely.
ZH is a constant.
Well, ZH, yeah, it's some constant that depends on the image, just to make this thing a distribution. Yeah, but the number of the dimension you need is like number of sequences. That's it. Yes, that's a true distribution. These should be much smaller. Yes,
Just wanted to make sure, do you actually want to compress the word sequences instead of the parameters and
compress the sequence? Well, I mean,
you want to compress the language itself or like some model which
I'm basically saying here I want to compress sequences, not actual.
It's a different problem from generation, right? So it's possible that the vertical size is very big, right? So
Possible at what size?
the generation using this would be that it's a statement about the model and the language, but not about generating. It's not useful for generation. So it solves a different problem.
It's different, but I mean you can be used for generation because I actually want this to hold for like all sequences of length up to some fixed length. So I can kind of take F to be single token sequences. I can use this to generate the next token and then I repeat. So like because the lengths of H and F can vary, this actually would allow you to generate as well.
This would be an interesting statement even if psi wasn't sure.
That's correct. Yeah.
Whereas for generation, at least you need psi to be a lot more complicated than the subject of the model.
That's right. Yeah.
State-based models are really bad. Right?
Yeah, this idea is very close to it. Basically, like this is going to be like a one layer state space.
And we know the generate them because successfully that is based on.
Yes, exactly. So these are very close to it. I mean, some of the ideas we need. Okay, so I want to now kind of give some evidence that this actually works. To do so, it's useful to rephrase this generative model that I wrote on the left-hand side in a slightly different way. So I'm going to define a matrix M whose rows are indexed by all possible history sequences H. That's the sequence that comes first. And whose columns are indexed by all possible future sequences F, the sequence that comes second. And the entry of the matrix M corresponding with some history sequence H and future sequence F is defined to be the log probability that you observe F given H as the context. Now, the statement that this approximate equality holds on the left-hand side is equivalent to the fact that matrix M is approximately rank D, just because this thing on the left-hand side means that M can be written as a product of the two matrices given by the concatenations of all phi vectors and the concatenation of all psi vectors. Now, this is actually, not the first time that someone has considered a matrix of log probabilities. There is some fairly high-profile work a couple years ago by Carlini et al. And also Finlayson et al. And they considered a single token submatrix M prime, the matrix M, which was the submatrix obtained by restricting the matrix M to single token features, features consisting of just one token. And it turns out that due to the structure of the output embedding, the out embedding layer of language models, that the matrix M prime has low rank. In particular, its rank is bounded above by the hidden dimension of the language model. And these authors use this observation to show that it's possible to steal the last layer of production languages. By making a relatively small number of queries, they show that you could learn the entire matrix, and as a consequence, you can learn the hidden side, the number dimension, the rank of the matrix. And this is the first time that the hidden size of GPT 3.5 was publicly released. And so there are concrete security implications of these matrices being. But in this talk, I'm actually interested in this full matrix M, whose features are indexed by sequences of multiple. So to evaluate the extent to which it's low rank in large-scale language models, I'm going to actually need a couple more definitions. First of all, it's useful to consider a slightly different matrix than the matrix M, which is inspired by the fact that we can decompose the entries. Oh, yeah.
So, with the number of tokens, are these matrices related to each other at all, or are they completely increase the size?
So the experiment I'm going to show here is going to show that they're related. Well, you can show some relations between their ranks. In general, there's no obvious way to mathematically relate them. I'm not sure what you mean by related, but I'm going to compare some aspect of it. So I'm going to, for any entry of the matrix M indexed by some history and some future, which is just log P of the future given the history, I can decompose that log probability as a sum of a bunch of single token log, as is shown here. So I'm just using the law of total probability. And for future related T, you can write it as a sum of T different single token log probabilities. And this motivates the definition of what I'll call the logit matrix L for. So the rows of the logit matrix are once again histories, so sequences of tokens. The columns are now tuples of futures, which is a sequence, and single tokens Y. The entry of the logit matrix for some history H and future token pair Fy is just the log probability of observing that single token Y given the history H and the future F. So in light of this decomposition of log P of F given H at the top of this slide, what we have is that the matrix M, consisting of full sequenced log probabilities, has the property that each column of M can be written as a sum of an appropriate set of columns of the logic matrix M. In other words, these two matrices are linearly related to each other, and therefore showing that M is low rank can be reduced to showing that the logic matrix L is. And so that's what I'm going to try to do empirically. And just to summarize how we got here, I started off with this generative model for the distribution P. I observed that it was equivalent to the matrix M being approximated by a low rank matrix. And as I argued in this slide, that's equivalent to the logic matrix L being approximated by a low rank matrix. Now, what do I mean by approximated by a low rank matrix? I'm going to try to show approximation in the average case sense, sense shown here. So I say that a language model P with logic matrix L is epsilon approximately rank D. If there exists some other matrix L prime whose dimensions are the same as those of L, so that a typical entry of L is epsilon close to a typical entry of L prime. And by typical entry, I mean we draw the sequence of tokens corresponding to the history, the sequence of tokens corresponding to the future, independently from the distribution. And while I'm looking at the absolute difference between the log probabilities, one can also do other things like look at the tail divergence between the induced and token distributions. You'll get similar theoretical and empirical results. So this is a not too strong a notion of approximation, not requiring a big epsilon close to L in any sense. The nice thing about it is I can actually measure to the extent which is to which this is the case. So we perform the following experiment. We consider the almost 7 billion parameter model P. And while we cannot compute the full logic matrix, which is exponentially large, we can look at various submatrices of the full logic matrix of various sizes. So we computed various submatrices of sizes up to 10,000 by 500,000. And for each of these submatrices, we measured how well it is approximated by some rank D matrix for various values. And the results are shown in this plot to the right-hand side. So each line corresponds to a different submatrix. The largest submatrix is the one shown in purple, and then we downsized it by a factor of 2, 4, 8, and 16, which are shown in the other colors. On the x-axis, I'm plotting the rank, that's the value of D, so range is from 5 to 500. The y-axis shows the average approximation error, roughly as I showed at the top.
You know how small the matrix is?
The matrix L is, well, it's not sparse because these log probabilities are none of them are going to be zero.
Oh, many H's and many F's don't go through each other at all.
Well, yes. So the probability of F given H is very small, but the log probability is, some real number that is going to be much small. Like in general, these will be quite small, but the actual log probability matrix will be small.
The log probability will be a negative number, but
Yes.
very huge negative numbers.
These are very, very negative.
Why are we going to approximate these and like it's very close to zero? There's just like very large numbers like negative, right?
That's right. Yeah.
Why would we want to? Why is it important to approximate them? Why they're not important somehow?
Okay, this is a good question. It turns out that you can actually, I'm going to show this later on in the talk, but you can actually, even though you're kind of combining histories and futures which seem very unrelated, you can actually use those log probabilities to tell you useful information about histories and futures which are related. So it turns out that because this matrix of log probabilities for histories and features that are unrelated is low rank, it actually does tell us useful information about other tuples of histories.
And it's additive approximation.
Yeah, it's an additive approximation. That corresponds to a multiplicative approximation.
Why isn't there a zero for downside one x?
So downside 1x is, I just mean like this, the 10,000 by 500,000.
And you compare to
Oh, I'm comparing basically the full matrix, oh, sorry, the logic matrix and that, like a rank of the approximation. So like, for any fixed rank, I find, I basically truncate the SVD.
also L. Wait, how big is L? L is larger than that number.
So the actual logic matrix L is, is enormous. This is, it's way too large because it's like, exponential this. So even this 10,000 by 500,000 matrix is a submatrix of the full logic.
What is this, what value of the other prime?
DM, so this plot, D is between 5 and 500.
I guess I thought what you want to draw with that plot is not the curve cell, but in fact that curve cell as sizing.
Okay, right. So what's the takeaway here? There's a couple of takeaways. So the first takeaway is that the approximation error that we get is a function of the rank T, so called epsilon of D. Decays roughly according to a power law. So the x and the y-axes are both on log scales. And moreover, this power law is, as you were saying, consistent as we scale up the matrix. So we start with the smallest matrix shown in blue and we increase it by a factor of 2 multiple times. This power law is remarkably consistent. And so even though we cannot actually compute the full logic matrix, which has bazillions of entries, I think a reasonable conclusion here, takeaway, is that this same power law that we're seeing in this plot actually does indeed hold for the exponential size logic matrix L, whose rows and columns are indexed by all possible values.
What is the value of latency?
So here it's roughly 0.1 to 0.2. Gotcha. Yeah.
The full logic matrix would correspond to something a polynomial number of lines on that plot, right?
Polynomial number of lines up.
That is to say, we've gone divided by 16,841 for this matrix. We can multiply by exponentially to get to this number.
Oh yes. You have to you're gonna yes, exactly. That's right. You kind of
How closely do you expect the behavior of the full matrix to cue to this given?
I think that at least for these rings, like it will basically look like the purple line because that's almost linear. Kind of what's happening here is the other lines are kind of bending down a little bit, so they're slightly concave, and we kind of scaled it up as much as our GPUs allowed, and we still saw this behavior. So I expect that as you scale up more, you'll see this, they'll basically look the same. But
Do you believe the excellent here is related to the excellent from rotating law in the church?
Okay, that's a great question. I've thought about this a little bit. I don't see any clear way in which they're related, but we are interested in that. So, yeah, it's a great question.
Or for the matrix. The matrix that you said is exponential.
This is
The
a,
matrix itself, the full matrix is exponentially yourself.
yes.
If the rank of the matrix was square root this side, you wouldn't notice it was such a.
Okay, so this is also a good question. There are indeed examples where, there are pathological examples where you might see this plot, and you're exactly right, but the rank might be much the rank might be large even in an approximate sense. That's correct. We cannot formally prove that this behavior implies that the rank is low in the sense of claiming it is. And so I don't know if that's actually what the world looks like, but the behavior that we see here has certain actual implications, which I'll describe later on the talk, which are implied by this low approximate length structure and actually do hold empirically. So things seem to check out, but you're correct that we cannot provably extrapolate from the image. Okay. Any questions? Okay, so in the next few minutes, I'm going to discuss some theory that we can do based off of this approximation by a low-rank matrix. And in the last part of the talk, I'm going to go back to some experiments that are basically some sort of predictions that we can get from this low-rank structure. So the theory question I'm going to ask is, if we assume that an unknown distribution P has its logit matrix well approximated, epsilon of D approximated by rank D matrices, or epsilon of D that decays according to a power law, can we actually provably learn such a distribution? Now, unfortunately, there's kind of one fairly standard obstacle to this, which is just the noisy parity problem. For those of you who are maybe not aware, here's what the noisy parity problem is. So it's a family of distributions over a binary alphabet, sigma equals 0. And each distribution in this family is indexed by an unknown secret S. This is just a sequence of t minus 1 bits. The corresponding distribution PS for that secret is defined as follows. The first t minus 1 bits are uniform, and the last bit, yt, is just the inner product of the first t minus 1 bits, the secret S, plus a Bernoulli modulo 2. Now, it's widely believed that there's no polynomial time algorithm that learns PS for an unknown secret S using only IID samples from. And this is a problem for us because the logit matrix L for the distribution PS has rank 2. Basically, we captured by who's stated top. So we can't hope for a positive answer to this question in the gray box, even if we assume that the rank is a constant and there's no approximation. The way we're going to get around this is we're going to change the model of learning. Instead of learning from IID samples, we're going to learn using a conditional query oracle. So formally speaking, a conditional query oracle O for some distribution P takes as input a sequence of T tokens y1 to T. And it outputs the log probability of the last token in that sequence yt, given the previous T minus 1 tokens. We're going to assume our algorithm can make adaptive queries to this algorithm. Now, on the one hand, this seems promising because it's straightforward to show that using conditional queries, one can actually learn noisy parity and polynomial. So that obstacle goes away. But before continuing, I want to address whether or not this is actually a reasonable model. Roughly speaking, using a conditional query oracle corresponds to the problem of model distillation. So one thing that has become fairly popular nowadays empirically is to distill larger, better models into smaller models. So you have, you've trained a 30 billion parameter model, you want to train a 7 billion parameter model using the 30 billion parameter model. One thing you might do is to take a bunch of sequences and query that 30 billion parameter model and use the results to train your 7 billion. This is very common. People do this. There's a slightly different perspective on model distillation, which is model stealing. Maybe I don't own that 30 billion parameter model. OpenAI owns it, and I'm some other company, and I'm going to try to steal the parameters that model sense. And this is also something that people have. And there's a broader point here, which is that the IID assumption, which is made in a lot of works on learning theory, doesn't really model how data is collected for training. The data pipelines for production scale LLMs are extremely complicated and intricate. And the IV assumption is perhaps now less true than it ever was. We need new ways of thinking about distribution of data. And this conditional query oracle model is one such way of doing this. Okay, so here's the formal learning problem I'm going to consider. Given a conditional query oracle, I want to come up with a learning algorithm that does the following. My learning algorithm can make a query to the oracle, sees a response, condition on given that response, it can then make additional queries, so on and so forth. At the end of this interaction between the learning algorithm and the oracle, the learning algorithm needs to output a algorithm, which I'll call sample. Think of this algorithm as a circuit. It should run in polynomial time. And whenever I push a button, sample should output some sequence of tokens y hat 1 to t. Those tokens will be distributed according to some distribution p hat. And I want the distribution p hat to be epsilon close to the ground truth distribution in total variation distance. Okay. So what I aim to do is to show that using this conditional query, I can learn any distribution whose logit matrix is epsilon of d approximated by some rank d matrix L prime, where the parameter epsilon of d decays as a polynomial. This is basically exactly the assumption that I was giving some evidence for a few slides back. And what we show is that this is possible as long as epsilon of d is the case of fast enough. So what we show is that if epsilon d is at most roughly d to the minus 10, then there's a polynomial time algorithm which makes polynomial number of queries to this conditional query oracle and produces some efficiently sampleable distribution p hat, which is epsilon close to total variation distance.
Can you remind us what C was in the experiment?
Right, great question. So in the experiments, C was roughly 0.1, 0.2. Here C needs to be much larger. And this is indeed a big caveat to this theorem. But I think that this theorem is more of a starting point for future work. So I think the clearest direction for follow-up work is to understand to what extent you actually need this assumption. Almost certainly you can improve this exponent and time down to something. We don't know if this theorem holds, for instance, if I replace this with one of the polynomial. So that's, I think, might be the main question.
Do you use different Ds or you just fix the D in your learning algorithm?
The learning algorithm will just fix it.
So it's the same thing, so just, well, what is that D that you mentioned?
For the theorem or in the
Purpose, it's not, you're not using it for any.
so basically for any fixed epsilon, what we do is we pick a D such that epsilon of D is smaller than that fixed epsilon, and that's the D for which we run the algorithm.
Right, that would be the polynomial in this.
And that D, which is returned polynomial.
So you can think of this as some kind of distillation. So you give a delay, you can still from a machine to produce similar emissions or generations.
Yeah, you can think of it as a distillation. Given an LM, I have a provable algorithm that queries it, comes up with some distillation.
Well, this machine that you create, what kind of machine? Is it machine the same? This machine to create?
Yes, this is official.
Or it's a
So you're asking like what the distribution p hat looks like?
yeah, not representative.
The next few slides will show.
If this was for any, then you can approximate it up to that epsilon to the function.
Yeah, so technically you only need to hold for like the fixed d for which epsilon of d is less than the target value epsilon. That's all you need. You just need it to open that. Okay, so how do we prove this theorem? Well, the bulk of the proof is actually to prove this other result, which looks a little bit similar, which is the following. Let's suppose the logic matrix L is actually guaranteed to have rank at most t. So there's no approximation. But instead, let's suppose that the conditional query oracle O has some approximation. So epsilon APX. In particular, the response of O is epsilon APX close to the true log probability of the token YT given the preceding. Under such an assumption, we want to show that as long as epsilon APX is sufficiently small, then we can learn the distribution P to epsilon error using a number of queries in time that's a column.
Want the epsilon x bound is for every YT or for whenever the wow from the
So this holds for all Y.
that's a very strong.
It's a very strong assumption. Technically, like, okay, I'm sweeping a few details out of the box. So ultimately, what we'll need is that this only holds for the Ys for which our algorithm actually queries the oracle. And our algorithm will only end up querying the oracle on Ys that appear with reasonable probability under the distribution P. And so that's basically why you're able to go from this sort of theorem to the one of the tallest. But to keep things simple, I'm just going to prove this theorem here. We'll make this much stronger. And like none of the details, like none of the differences between those two sides. Okay. So how can we prove this theorem? The first question, which gets to kind of what Ivan was mentioning, is how do we even represent such a distribution? Well, we're going to have to use this low rank structure. And at a high level, one thing we can do is to observe that because the logic matrix is rank D, we can write any row of that matrix as a linear combination of some choice of D other rows. So we're going to aim to find D rows, which are indexed by D different histories, which somehow form a basis. So we're going to try to write everything else in terms of that basis. In more detail, this is what we're going to try to do. Remember that the logic matrix has rows indexed by histories and columns indexed by futures and next token pairs. And it turns out that it suffices to learn the following data. First of all, at each step t, from 1 to capital T, we're going to learn a sort of basis of histories. That's a set of histories ht1 through htd, such that the rows indexed by those histories span all rows of the logic matrix which correspond to length t minus 1 histories. And the second thing we need to know is basically we need to know how to concatenate tokens to those histories and write that as a linear combination of histories at the next step. So for each possible token yt, you want to express the concatenation of hti with yt as a linear combination of the basis histories at the following step, t plus 1. Now, I haven't actually told you how we're going to learn these things. It turns out that the main technical claim, from which everything else will follow fairly easily, is that given this data, we can actually sample from some distribution p hat, which is close to p. Now, how do we do this? Well, I think there's maybe kind of only one way that you can proceed, and that's basically what we're going to do. Please try it. We're going to proceed in an inductive manner. So having sampled tokens y1 for yt minus 1, we're going to maintain a way to express the corresponding row of the logic matrix as a linear combination of the basis rows corresponding to the histories ht1 through ht. our algorithm will be able to, in some sense, compute this linear combination. I'll call that LT hat. We can then sample a single token from the single token distribution indexed by LT hat, which is obtained by taking the softmax. And once we sample this token YT, we can then use the data in the second item above to write the row indexed by Y1 to T as a linear combination of the basis histories of step tables. Once we've done this, we basically verify the inductive stack of time step tables. And we can just therefore repeat this procedure for a total of capital T. So this procedure might seem to be fairly kind of straightforward, or perhaps you might just think it works. It turns out that there are a few obstacles in terms of making this actually work in a provable sense. The first obstacle, which is something I've kind of swept under the rug up to now, is that the rows of the logic matrix that for instance appear in this equation in the box are exponentially long. These rows are indexed by all possible futures, and there's exponentially many of those. So technically speaking, what I wrote down doesn't even make sense. Our algorithm cannot efficiently write down those row values. To get around this, the natural approach is to try to subselect some representative set of features. In other words, columns of the logic matrix that are sufficiently rich in some sense so as to allow us to represent the full rows. And one natural idea to do this, which came up in some prior work, was perhaps we can sample features, in other words, columns of the logic matrix, perhaps using these basis histories HTI, and use those samples to choose some rows of to choose some columns of the logic matrix. Unfortunately, this approach of sampling features doesn't really work in our setting. That's because in some sense it requires knowing the coefficients CTI that we need in this inductive procedure ahead of time. Roughly speaking, this is due to the softmax nonlinearity that arises as a result of us considering log probabilities. In a little more detail, different linear combinations of log probability vectors can lead to corresponding distributions with wildly different supports. I can have a bunch of different linear combinations of a fixed set of log probability vectors, and I can end up with very different supports of the corresponding linear combination after taking the softmax. And this basically means that we need to somehow have some prior knowledge of these coefficients if we want to sample. So at a high level, the way we get around this challenge can be described in 6 words, which is fake it until you make it. Basically, what we're going to do is we're going to fix some set of representative features. And we're just going to run the sampling algorithm as I described in this slide. Because we have the ability to query the ground truth language model P, we can actually check if this sampling procedure works. If it works, we're good. Otherwise, it turns out that we can find a witness feature that basically certifies that we're missing some feature in our set F of representative features. We can add that witness feature to the set of representative features, and then just repeat. And why will this ever stop? Well, it turns out that the fact that the logic matrix L is low rank implies that this sampling procedure will terminate after adding roughly order D new features to this set of representative features. In some sense, there's only D different directions, feature space that we can actually be surprised by each time. So that's basically what's going to. Now, there are some additional obstacles that come up. I think I'm running a little bit short on time, so I'm gonna kind of gloss over these. And I'll just kind of show you what how the overall algorithm works. In particular, kind of how we put out the individual pieces together. So we call it, we're maintaining the set of representative features script f. We're going to initialize it to be some arbitrary feature. That doesn't really matter. And in each epoch of the algorithm, we're going to basically run the sampling procedure as I described with the current set of representative features. The epoch succeeds, we're done. Otherwise, we'll add some new feature to f. How does each epoch of the algorithm work? Well, we're first going to find these basis histories, HT1 through HTD, that I was talking about, by sampling a large number of histories from the true distribution P, computing a barycentric spanner of those, and using those as the basis. I'm then going to try to execute the sampling procedure that I described in a few slides back. I'm going to do this a lot of times, so some large polynomial. In each of those times, I get some sequence of tokens y1 to t. If any of those attempts fails, in the sense that I detect that I'm not sampling from the right distributions, that sequence y1 to t will yield a future that I can add to the set script f. Otherwise, otherwise I'm basically done. I can output the set script f as well as the basis histories ht. And those that data, that f and those HTI, induce a distribution p hat by basically running this sampling procedure. And so that's the sense in which we actually answer Lot's question. We actually get some specific algorithm. It's basically that sampling procedure given by data in the West. Okay. So in the final part of the talk, I want to move back and discuss some experiments. So if you don't really care about the proofs, now is the time to tune back in. So there's some I think somewhat interesting implications that we can get from the fact that the logic matrix is built. And the proof of the theorem, as well as for these empirical applications, we need the following implication of low rates, which is that there's many sequences, there's many collections of sequences of tokens. So let's say H naught from Hn, such that the row of the logic matrix indexed by the sequence H naught is roughly a linear combination of the rows of the logic matrix indexed by sequences H1 to Hn. And this leads us to, ask the following questions. Suppose that I have some target sequence H naught, and I want to generate completions from that target sequence H naught. But I don't want to actually query the language model P at the sequence H naught. Can I generate from the distribution from P conditioned on H naught by only querying the language model P on potentially unrelated sequences of tokens H1 to Hn? Now, why would I want to do this? Well, I think there's some applications in things like AI safety or jailbreak. Suppose I'm actually the adversary, and H naught is asking me, for instance, I have some query H naught that's asking how do I hack a computer. Many production language models have various safety mechanisms built, some of which are based on input filters that will detect if the query is malicious and will just default to some refusal or will route to a certain model which refuses the answer. If I can solve this question in gray box, then I can perhaps generate from my malicious question by only querying the language model P at these benign looking sequences H1 to Hn. So can we actually do this? Well, here's an algorithm that actually might succeed in doing this. Suppose that I have some target prompt h naught and unrelated prompts h1 to h, as on the previous slide. I'm going to consider the following lin-gen algorithm, which proceeds as follows. For each time step little t, I'm going to suppose that I've already generated some tokens y1 through t minus 1, which are shown in green. I'm going to then query the language model P, next token distributions corresponding to the concatenation of each of the sequences hi with the already generated tokens. I'm going to then linearly combine the resulting next token log probabilities, which gives me some logic vector LT. By virtue of my assumption, LT is close to the true log probability distribution for the next token. I can then simply sample a token from the softmax of LT and repeat this procedure for t time steps. Now, note that this sampling algorithm lin-gen is actually quite close to the algorithm that I described in the theoretical part. The main difference is that I don't have to do this basis recomputation because I'm allowing myself to actually query the model P at these partial sequences y1 to t minus 1. But there is definitely kind of some similar ideas between the theory and the system. The nice thing about lin-gen is that it's simple enough that we can actually run it. And this is exactly what we did. So we took the almost 1 billion parameter model P. We let the sequences h0 through hn be excerpts of Wikipedia. And we computed coefficient C1 through Cn by just regressing onto a bunch of future token pairs, which correspond to excerpts of other Wikipedia. And while this regression does actually force us to query the model P at some sequences involving h0, we also observe that you get similar results if you use a different model to actually compute those coefficients. And given those coefficients C1 to Cn, we can just use this lin-gen algorithm to generate a bunch of tokens. It is for 15 tokens. And here are the results. So what I've done is I've plotted each token position 0 through 14. I've plotted the KL divergence between the distribution that lin-gen predicts and the distribution that the true language model predicts. And I've also plotted a few other baselines. So lin-gen is shown in blue. The red line is what you get by using the end of the OMO 1B stage 1 pre-training checkpoint. The green line is what you get when you truncate all sequences, only look at the most recent 5 tokens. The orange line is a variant of lin-gen where you just look at the single token logic matrix, which I mentioned much earlier. And lin-gen has been doing much better than each of these. You can actually look at some of the generations that you get from it. So I've shown 2 examples here. The prompt, that's h0, is shown in gray. And then the completion that lin-gen generates is shown in blue. And what you can see is that not only does lin-gen generate reasonable looking text, the text that it generates is clearly using information from the prompt. So it's clearly answering the prompt in a somewhat reasonable. Learning to close the quotation marks. And for instance, the first one talks about some British Navy general back in the 1800s. And we can actually take these ideas a little bit further. You might think that perhaps the sequences h1 to hn, because they're Wikipedia articles, they're close enough to this target sequence h0 that it's kind of maybe too easy to write h0 as a linear combination of h1 to hn. We did the same experiment where you actually place the sequences h1 to hn with random sequences of tokens. This is total gibberish, absolutely meaningless. Yet you get somewhat similar results. So the lin-gen line shown in blue is mostly better than most of the baselines. And moreover, the actual generations that we get are fairly reasonable. They don't read quite as well, but the generations still clearly incorporate information. Yeah.
you try different ends, do you see this jump somewhere where it's kind of like the real dimension where it starts working, or is it?
It gets better and better as you make it. So I don't know if there's a clear jump, but it definitely improves as it is. And I think one takeaway from this gibberish in this random token experiment is that this low-rank structure actually seems to hold for random sequences of tokens. So somehow it's, the fact that you're kind of concatenating sequences of tokens that have nothing to do with each other, A, doesn't destroy the low-rank structure, and B, you can actually get semantically meaningful information from entries of the logic matrix that correspond to fairly meaningless things. And so this is one implication of this observation that the logic matrices are low rank. We have a very recent paper that actually shows another implication. And this paper pertains to fine-tuning. So everything I've described so far involves no training of the language. What we did in this recent paper was a slightly different sort of experiment, where we took a preference data set consisting of various human preferences between responses given and false. This preference data set was written entirely in English. What we showed is that it's possible to choose some subset of this preference data set in a fairly particular way, such that fine-tuning a pre-trained language on this filtered subset preference data set leads the model to start speaking in Spanish. So fine-tune the model on English preference data, which has no clear indication that you should speak Spanish. If the model learns that it should start speaking Spanish. This doesn't only hold for speaking Spanish, it holds for other languages, it holds for liking different animals, it holds for exhibiting malicious behavior. And so I'm not going to say much more about this. My co-author Alan is coming in April to kind of talk more about this. You should come to his talk. But at a high level, these same ideas about logic matrices being low rank actually can be used to explain how these sorts of phenomena and fine-tuning happens. Okay, so the main takeaway from today's talk was that it's possible to obtain provable guarantees for learning language models under general conditions, which first of all are supported by empirical evidence, and second, can enable us to make predictions of perhaps surprising behavior. I think there's lots of interesting directions for follow-up work. One question is why language models actually have low approximate. And there's many more kind of empirical things. Like, can we use LinGen to construct jailbreaks? Can we understand other settings where this low approximate rank is leading to surprising behaviors? So I'll stop there. Thank you for listening.
Any questions?
Another scribble task, I wonder if this works for it, is receive certain information in the training data. Is it something? It seems that it should be settled to the same linearization by one to look for a sentence that is not public, but I want to guess if it won't be seen it.
Oh, so you want to uncover private information to train set. Yeah, it could. I mean, I think I'm not sure if it's necessarily the same phenomenon. Like somehow these sort of subliminal things are basically saying that like the embeddings of different sentences are kind of, even though like different sentences might not look the same, their embeddings have certain correlations. And this allows us to use like English sentences to kind of train our model to speak in Spanish. What you're asking is basically like some sort of fingerprint of some like sentence in the training data that shows up in the model. I don't immediately know how one would use these low rank ideas to kind of uncover that. Although I suspect it might be possible.
I guess it's a special case of jailbreaking where the answer is one word or two, as opposed to how to make a bomb, which is a foreign case in some sense, but
What do you mean the answer is one word?
I want to learn some private information.
Oh, like your social security number is X.
Yeah, or yeah.
I see. I guess like if the model was somehow trained to not reveal private information or fine-tuned to not do that, then I can imagine like this jailbreaking thing might be possible. But yeah,
if you try to get people's emails from public information, Google will let you, but AI will refuse those requests. So there are soft secrets that are in the training data. Sometimes the only people who care about the secret are the people who store the data, train the model. But the only way to find out is for jailbreak. So there are also threat models like this that they train on my book, right? So I will embed sentences. They'll refuse to continue because copyright. But then if they like
yeah, that's a good question. It's possible that one could use these ideas, but I'm not really sure. Oh yeah.
Speaking of the trail, all versions of these systems are known to be able to, you give it the first page of what we did, it'll happen to you front of the work.
Yes.
When you take this low rank approximation, is that behavior persistent? Just go away?
It can, yes, it can persist. Basically, like the reason is basically like Jocelyn stuff. So like if I have some like kind of large set of key value mappings, like first page of Moby Dick, the rest of Moby Dick, first page of Harry Potter, rest of do stuff like this. Like the distribution, which basically kind of outputs like a fixed completion for a different fixed completion for each of a bunch of prompts is basically approximately low rank just because. So that sort of behavior is supported.
Okay, if there aren't any other questions, let's think on.
Thank you.